All right, so in our 20-second lecture real analysis, we're going to pick up where we left off last time. So I'll give you a summary of what we did last time. You might recall that we started by defining the exponential function of base b, denoted in either one of these two ways, on the rational numbers. So we know what b to the x means for a rational number. Essentially, we have we have integer powers of b, and we have roots of b, and we can combine that to define the xth power of b as long as x is rational. And in particular, we proved this is a continuous function. Okay, so this is a continuous function from the rationals to the positive real numbers. And our goal was to extend this function to a function defined on all of the real numbers continuously. Okay, so of course we can just sort of arbitrarily choose values of this exponential function on the irrational numbers. We want to do this in a natural way such that we maintain continuity when we do the extension. So we have a nice continuous graph you can think of intuitively, like you would see in pre-calculus. Okay, so this is the problem. We have a continuous function on some domain. We want to extend it continuously to a larger domain. But to caution ourselves, so we have some sense that this is possible in this case because we've seen what the exponential function looks like in pre-calculus. We're sort of assured that this thing exists and has a continuous function. We worked with it in calculus. This all seems sort of rather obvious, but I wanted to point out in the last lecture that it's not actually obvious because there are cases where you have continuous functions which cannot be extended to a larger domain. So we looked at a couple cases, simple cases of continuous functions on the non-zero real numbers which could not be extended to continuous functions on the real numbers. And we tried to examine what was wrong with these functions that made it impossible to extend them to continuous functions. And we decided that the property they had is that they sent points which were close together in the domain of the function to points that were far apart. Okay, so in some sense, even though they were continuous at points at any particular point in the domain, there were nevertheless ways in which points could become close together. In particular, they could become close to points that are not in the domain and have the images of those points be far apart. So to rule out bad examples like this, we defined a notion called uniform continuity. Okay, so uniformly continuous functions are continuous functions such that such that points that are close together in the domain always get mapped close together, essentially. Okay, so we define that carefully in not such broad and ambiguous terms in the last lecture. And we looked at a bunch of examples, so hopefully that concept was clear. And in particular, we proved that our exponential function, as defined on the rationals, is uniformly continuous as long as we looked at any bounded subset of the rationals. Okay, so if we restrict our rationals to lie in some particular finite range, then the exponential function is uniformly continuous. Okay, so this is sort of the key thing that's going to allow us to extend our b to the x function from the rationals to the rest of the real numbers. So in this interval from negative m to m, right, you have a whole bunch of irrational numbers arbitrarily close to the rational numbers in there. And so across all of those irrational numbers, you have this uniform continuity. So rational numbers that are getting close to those gaps in this domain, those irrational numbers, their images are close together by this uniform continuity, and that's going to allow us to extend this b to the x function. So to do that, what we showed is that if you have a function which is uniformly continuous on bounded subsets of the domain, so if we take the domain and we intersect it with some finite ball, if your function is uniformly continuous there, then your function has to preserve Cauchy sequences. So in particular, well, our b to the x function has that property that if we take our domain, we intersect with some and we just looked at some finite part of the domain, our function is uniformly continuous. That means b to the x has to preserve Cauchy sequences. Okay, so the conclusion is that b to the x maps Cauchy sequences of rational numbers to Cauchy sequences of real numbers. And what that allows for us to do is to define b to the x for any x in the real numbers by taking a rational sequence going to x. Okay, so this sequence converges, so it's a Cauchy sequence, and therefore it gets mapped to a Cauchy sequence. So that means b to the ri is a Cauchy sequence, and therefore it has a limit. And so we can use that limit as the definition of b to the x. Okay, and this is the natural definition if we want this b to the x function to be continuous, because a continuous function has to respect limits, right? If this b to the x function is going to be continuous, it's going to have to take this sequence of rationals going to x, the image there, that sequence is going to have to converge to the image of this x under the exponential function. Okay, so this is really the only kind of natural definition we could come up with here. So a couple issues, natural issues to address about this this definition is whether, so first of all, whether this definition here depends on the rational sequence that approaches x. So it would be sort of unsightly if we would get different definitions of b to the x for different rational sequences approaching x, right? Take one sequence approaching x, take another sequence approaching x. If you get a different limit there, that's kind of ugly. You're kind of making this arbitrary choice by just taking, sort of a random rational sequence. It'd be much cleaner if any rational sequence is going to converge to the same limit. So we would like to address that. And intuitively, that should be the case. So we'd like to address that. And we also need to know whether, and this is the sort of the main problem, whether with this definition, the resulting function so defined is continuous. And that will be addressed by the first main theorem that we discuss in this lecture. So the theorem is the following, that if we have a continuous function, okay, defined on some domain A, this domain A can be an Rm. So we have a continuous function, and let's say it has the property that it takes Cauchy sequences to Cauchy sequences, okay, just as we've discussed above. So we know our b to the x function has this property, so this theorem will be addressing, in particular, this b to the x function. Well, then what we're going to see is that there's a unique continuous function. So we'll call this f bar, which is defined on a bar. Okay, so we can extend our function to the closure of a in a natural way. So this function on the closure has the property that when we restrict it to a, it's f. Okay, so it really is extending our original definition, our original function, and it's continuous. Okay, and there's only one such function, so there's only one way to do this continuous extension. Okay, so this function f bar is called the continuous extension of f. So if we prove this theorem, then that immediately tells us that we have a well-defined exponential function on all of the real numbers because the closure of the rationals is the real numbers, as we've seen. Okay, so this theorem will address the main question that we started out with at the beginning of the previous lecture. Okay, so let's look at a proof of this theorem. All right, so our main goal here is to construct this function here. So we'll construct this function, we'll show that it's unique, and we'll show that it's continuous. So to define f bar at x, which is in the closure, well, we'll just take any sequence which converges to x. Okay, so this is just like, we're just sort of mimicking what we already discussed in the b to the x case. So take any sequence xk in A such that xk converges to x. So this is a Cauchy sequence. So f of xk is also a Cauchy sequence by our assumption. So thus it has a limit, and we can use that limit to define f bar at x. So we have a limit, therefore limit of this sequence xk makes sense, and we define f bar at x, okay, so this is a definition, as the limit of that sequence. Oh, therefore, missed an E. Okay, so that's the definition of our f bar. Now, the first thing we're going to address is that this definition is actually independent of the sequence which converges to x. So we claim that this definition does not depend on the sequence. So if xk converges to x and say xk prime converges to x, then the limit of f of xk is equal to the limit of f of xk prime. And the argument that I came up with for this is very, very simple, but it's a little bit of a trick. So what we're going to do is we have these two sequences converging to x. What we're going to do is create another sequence which converges to x out of them, sort of a composite sequence. So consider now, or I guess I should say, to see this, consider the sequence x1. So we're going to interleave the sequences here. So we have x1, x1 prime, x2, x2 prime, x3, x3 prime, etc. There's actually an exercise you did for homework. It's back in the first section on sequences in the text, and it showed that if you have two sequences which are converging to the same limit, and you do this this interleaving like this of the sequences, then this sequence also converges to the same limit. So what we have here by that exercise is that this sequence also converges to x. So by a homework exercise, this sequence converges to x. To x also. So therefore it is Cauchy. And so by assumption, so again, we're going to use our assumption, the sequence of f values. So if we do f of x1, f of x1 prime, f of x2, f of x2 prime, etc., also is Cauchy. Is also Cauchy and thus convergent. But see, the thing is, so what we're trying to do is show that the f of x's and the f of x primes, that they have the same limit. But now these are those sequences are subsequences of a convergent sequence. So they both have to converge to the same thing. So since f of xk and f of xk prime are subsequences of this convergent sequence, they converge to the same limit. They converge to the same limit, and so we have that the limit of f of xk is equal to the limit of f of xk prime as claimed. All right, so a little bit of a trick there can get you around having to mess around with epsilons and deltas, which I think is preferable if you can avoid it. So moving now into the claims in the theorem. So we're going to show first that f bar extends f in the sense that its restriction to a is the function f, and we'll show that that extension is unique as long as the extension function is continuous. So we'll now show that f bar is an extension of f, and that such an extension is unique provided it's continuous. Okay, so to see that, so we just have to see that f bar of some x, which is in A, is equal to f of x. So if x is in A, take a sequence xk from A such that xk converges to x. Well, then f bar at this x is by definition equal to the limit of the f of xk's, but the limit of the f of xk's is just equal to f of x because f is continuous. So this equals f of x using the continuity of f. Okay, so this implies, thus f bar restricted to A is equal to f. So now, to see the uniqueness, suppose that G and H are continuous functions. So let's say G and H, they're continuous on A bar, such that G restricted to A is the same as H restricted to A, which is the function we started with, f. Then so we'll just have to show that these two functions are equal to each other. So then if x is in A, clearly g of x equals h of x since they're both equal since both are equal to f of x. If x is in a bar but not in A, then x is a limit point of A, then x equals the limit of some sequence where xk is in A. So now using the continuity of G and H, so now from the continuity of G and H implies, so we have G at x is the limit of this sequence, so that's the limit of G of the xk, but those xk are in A, right? And on A, our G is just f. So this is the, our G is just f, which is also h. So this is just the limit of h of xk. And again, using the continuity of h, right, since this sequence is going to that, the h's also have to go to the h of x. So this is equal to h of x. Thus, G is equal to h. Okay, so any two apparently different continuous extensions of our function f are in fact equal. Okay, so there can be only one. So the only thing that remains, so the only remaining point is to see that f bar is continuous. Okay, so the way to begin to see this is to use what's right in front of your face, which is the definition of f bar. So in that definition of f bar, we have some sequence xk of things in A, right, going to x, and this x doesn't have to be in A, right? It can be in a bar. But if we have this, then the f of xk's, right, just by definition, go to f of x, or excuse me, we have f bar here, right? So we have f bar. I mean, this is really, right, the f bar on xk is the same as f on xk, right? Because f bar is an extension, so it doesn't matter whether I put f or f bar here. We'll just stick with f bar to keep things uniform. So this looks like a kind of weak form of continuity for f bar already, right? So basically this is saying that if you have things in A close to x, then the images are going to be close to f bar of x, right? The images under f bar are going to be close to the image of x under f bar. Okay, so it's not that, so what we want to say is that for any x's in a bar that are close to this particular x, that the images are close. Right now we have a slightly weaker form of that. So if anything close to this x in A, then the images are going to be close. Okay, so we want to upgrade that from A to a bar. So I'm going to make first a note out of this observation. So the first thing, so to do this, to see this, we first note that the definition of f bar tells us that f bar has a weak form of continuity. Okay, so I'll make a formal definition of this. So for any C in a bar, given epsilon greater than 0, there is a delta greater than 0 such that if x is in A, not an A bar, if x is in A and the distance between x and C is small, less than that delta, this implies that the distance between f bar of x and f bar of C is less than epsilon. Okay, and so why is this? So if this were not the case, this is actually a fairly typical argument we've seen before. So this is really just the same argument that you give to show that the sequential definition of continuity and the given book definition of continuity are the same, or are equivalent. So if this were not the case, so there would be some epsilon for which this wasn't true. No matter how you pick delta, you'd have a violation of this inequality. So if this were not the case, there would be an epsilon greater than 0, or I guess I should say there would be a C in A bar, be C in A bar, and epsilon greater than 0. There'd be C in A bar, epsilon greater than 0. And what I'm going to do is, for any delta, you would have a violation of this. So in particular, for delta equal 1 over n, there would be some x within that 1 over n of our C, which violated this inequality. Okay, so you'd have a C in A bar here, an epsilon greater than 0, and then you would have an xn and xn in A, such that the xn and C were within 1 over n, but you have a violation of the inequality, the epsilon inequality. So f bar at xn and f bar at C are not close together. Okay, so then it's clear Okay, so in this case, it's clear that xn converges to C, right? So these are getting less than 1 over n. We can make 1 over n less than any given epsilon. All right, so it's clear that we have that, but we don't have f bar of xn, which remember is just f of xn because these xn's are in A. So we don't have this going to f bar of C. Right, because these f bar xn's are not getting arbitrarily close to f bar of C. And this is contrary to the definition of f bar. Remember we showed above that no matter what sequence in A you take going to C, the f bar of C is the limit of the f of xn. Okay, so we don't have that, which is contrary to how f bar of C is defined. Okay, so that contradiction shows that this statement here is true. And maybe I'll highlight this statement. Maybe I should make my highlighter bigger. Okay, so we have that. All right, so now we'll see that continuity, well, we can use this to boost ourselves to true continuity. Okay, so let me star that. So we will use the red star to establish continuity of F bar on A bar. So let C be something in A bar and epsilon be greater than 0. All right, so we need some idea for how to do this. Okay, so we want to make F bar of X within epsilon of F bar of C by making X sufficiently close to C. So let's say we have C here. We want to prescribe some delta such that when things are within that delta of C, we have this inequality between the F bars. So we know we can do this for X in A. Okay, so we know that, so if X is in A, right, we know by, so we can find, we can do this, so we can do, if X is in A, that's by star. Right, that's what we said. So if any X in here is in A, and we can find a delta such that any X in here that's in A is the images are sufficiently close. So the problem is going to be when you have an X which is in A bar but not in A. So if we have X here in A bar but not in A, that's going to be the problematic thing. So how close does this X in A bar but not in A have to be to C in order to have this? Okay, well, if X is in A bar, what does that mean? That means X is the limit of some sequence in A, right? So if I draw a little ball, or to say it another way, this means that X is a limit point of A, right? So there's going to be, let me see, so there's going to be some, say, Z. So this Z here is in A. So we're going to be able to, if we have this X in whatever ball around C, whatever size delta ball we decide to pick, inside that ball, we can draw a ball around this X, which stays in that ball. And then inside that ball, we're going to have some Z in A, okay, because this X is a limit point. But then this Z is in A, it's in this little ball, that means it's in this big ball. And so that means that this, this Z, right, so the F bar of Z, that's going to be close to F bar of C. But we can also make this blue ball here small enough so that the value of F bar at X is close to the value of F bar at Z, right? Because this X is something in A bar, and our thing star, and our red star, again, this is by red star, we can just restrict things close enough to this X such that whenever you have anything in A within that prescribed amount of X, then the F bar images of them are close together. And this will allow us to do a triangle inequality argument, right? So we'll be able to say that F bar of X and F bar of C, they can't be separated by more than this. So F bar, just insert F bar of Z in there. And so then to make this quantity less than epsilon, we just have to make each of those less than epsilon over 2. So ultimately what we need is this z in A to be close enough to C to respond to an epsilon over 2 challenge in this star, in that star statement above, right? So you have z in A over C in A bar. We need this z to be close enough to C to respond to epsilon over 2 challenge. So we're going to want this big ball here around C to be the delta which responds to an epsilon over 2 challenge. And then we'll make this, this blue ball in here around our x, we'll make that small enough to respond to the epsilon over 2 challenge of star for this point x. Okay, so we have the epsilon over 2 challenge around C, that's our starting delta ball, and then this ball here will have to be small enough to respond to the epsilon over 2 challenge around x and fit inside of this original delta ball. Okay, and then once we do that, then we'll pick a z in that ball around x. That z will have to both be in the small ball and in the bigger ball. So it's in the small ball, so we have this quantity is less than epsilon over 2. It's in the bigger ball, so this quantity is also less than epsilon over 2. And then triangle inequality gives us that the quantity we're fixated on is less than epsilon. Okay, so that's kind of the setup there. Okay, so we'll let epsilon be greater than 0. So then, by star, there is a delta greater than 0, such that when x is in A, and the distance between x and C is less than delta, those things imply that f bar of x and f bar of C are separated by less than epsilon over 2. Okay, so in particular, x in A and x less separated from C by less than delta implies that f bar of x and f bar of C is less than epsilon. All right, so ultimately, with this epsilon greater than 0, we want to say that any x within delta of C implies this, right? But right now we have the restriction that if x is in A and within delta of C, then we have the inequality we're looking for. So all we have to concentrate on is x in A bar minus A. Okay, so thus we only need to consider x in A bar minus A. So suppose x is in A bar minus A and x minus C is less than delta. Okay, so then since the delta ball, since the delta ball around C is open, and by red star, there is an eta greater than 0, such that the ball of radius eta around x is contained in the ball of radius delta around C. And if z is in that eta ball around x, and z is in A, then the distance between f bar of z and f bar of x is less than epsilon over 2. Okay, so each of these statements, this ball is open and by star, they're each going to give us a certain number back, right? So since this ball is open, right, we can find some number such that, say, eta 1, such that there's a ball of radius eta 1 around x, which fits inside this larger ball. Right, so the picture is just the picture I had drawn before. We have C here, you have X here. You can draw some ball around it that lies in that bigger ball by the openness. And also, by the statement star, for this given epsilon over 2, I can find an eta 2 ball around X, such that whenever you have something in A and in that eta 2 ball, then the separation between the images of z and x under f bar is less than epsilon over 2. Okay, so I might have a different ball of radius eta 2, but then I can just take eta to be the smaller of those two. Okay, so we get possibly different radii balls for each of these, but then you can just take the smallest one and they'll satisfy both conditions. Okay, so we have that, and now what we're going to use is, I guess, again, using my picture. So here's x, we have our ball here. Since x is a limit point of A, right, it's in the closure of A minus A, so it must be a limit point, we can find some z which is in A in that ball. Okay, so since x is a limit point of A, there is indeed a z in A such that z is in the eta ball around X. So in particular, so thus we have that f bar of z minus f bar of x is less than epsilon over 2. But also that z is going to be in the delta ball around C. But since the eta ball around x is contained in the delta ball around C, we also have z in A and z in that delta ball around C. So the separation between f bar of z and f bar of C is less than epsilon over 2. So therefore, the separation between f bar of x and f bar of C is less than or equal to f bar x minus f bar z in absolute value, or length, plus length of f bar z minus f bar C. That's less than epsilon over 2 plus epsilon over 2, and that's equal to epsilon. Okay, so our given epsilon, no matter what x we took in that delta ball, we found the separation between the images there is less than epsilon, so that proves the continuity. Okay, so that's a rather longish proof there, but the payoff is we have this rather general result about extending continuous functions to their closures, and just a particular case of that is our exponential function. So now, as a corollary, our b to the x, so let's say, so corollary so b to the x is a well-defined continuous function on R for any b greater than 0. Okay, so this is one way to define the exponential function as a real function defined on the whole real line. There are other ways to define b to the x. So the other way is to first define e to the x via power series, and then you can define b to the x in terms of that e to the x. So that's a rather different way of going about things. Another way is you can define, if you define the integral first, you can define the natural logarithm as the definite integral of 1 over x, and then define e to the x in terms of the inverse of that, and then you can define b to the x for any general x from that. Okay, so, but any one of those roots is rather involved and involves some sort of general theory. Is sort of, either involves power series or integral, the integral, and both of those things, use quite a bit of background and preliminary work to define b to the x. So either way, it's not simple, and this is just one approach, probably the least the least often utilized approach to defining b to the x. So what I don't want to lose track of in this whole discussion, so what I want to note here, is the role of uniform continuity in this whole discussion. So the notion of uniform continuity notion of uniform continuity played a central role in the above discussion, and so hopefully indicating the importance of this notion. So just to recall, the uniform continuity came into play when we saw that our exponential function was uniformly continuous on bounded subsets of the rationals, and that implied that the exponential function took rational Cauchy sequences to Cauchy sequences. So this exponential function defined on the rationals preserved Cauchy sequences, and that allowed us to do the extension. Okay, so the uniform continuity really was kind of key there. So hopefully this gives you some sense of the importance of this notion. So this notion comes up in other ways in more, in further discussions in analysis. So I want to talk just a little bit more about this notion before we close this lecture out. So remember, we saw there are continuous functions which are not uniformly continuous, but there were a number of examples where if we had a continuous function which was not uniformly continuous, we could restrict the domain of that function suitably so that the function did become uniformly continuous. So we saw there are continuous functions which are not uniformly continuous on certain domains, but became so upon restriction of the domain. And so the basic question is, can we say anything general? So can we say something general about when a continuous function on a certain domain is uniformly continuous? And maybe based on your own intuitions about certain kinds of sets that we've discussed, it might not come as a surprise that, in fact, a continuous function on a compact subset of Euclidean space is always uniformly continuous, and that is the content of the next theorem. So we have the theorem that continuity plus compactness implies uniform continuity. So if we have a continuous function on a compact set K, this is fully general compact subset of Rm, taking values in Rn, then this function is uniformly continuous on K. So let's take a look at the proof, and that'll be it for this lecture. So just first of all, remember what uniform continuity means. This means that we're going to be given an epsilon, and we're going to have to say that as long as any 2 points in K are sufficiently close, okay, so we have to identify some delta such that as long as x and y are only separated by less than delta, then their images are separated by less than epsilon. Okay, so the uniformity is that there's a single delta such that no matter what point in K I pick, the delta ball around that point, every image point in that delta ball has to be within epsilon of f of x. Okay, so that's what we have to show here. So we need to start our proof with let epsilon greater than 0 be given. So this is our epsilon to beat. And what do we have here? So all we have is continuity and compactness. So we have an epsilon greater than 0 given, and okay, so we have continuity. Well, that means, right, given epsilon greater than 0, then for any point in K, there's going to be some delta which possibly depends on that point, such that the delta neighborhood around that point is mapped within epsilon of the value of the function. Okay, so by continuity, or I guess I should say for any x in K, by continuity, there is a delta, and I'm going to say delta sub x to remind ourselves we just have continuity at each point in K, so this delta might vary depending on x. Right? So I mean, it's our ultimate goal in the uniform continuity to find a delta which does not vary with x. So by continuity, we have a delta depending on x, potentially. So delta sub x greater than 0, such that when x and y, so distance between x and y is less than that delta x. Okay, x and y in K, of course. That implies that the distance between f of x and f of y is less than epsilon. Okay, now actually, I should be a little bit, I should allow myself to be a little bit more flexible than this, right? Okay, so we're trying to write a proof. I'm trying to kind of walk us through the thought process here. So, I mean, this would be the natural thing, right? Just the straightforward definition of continuity gives you this. But in fact, you can get this for really any positive function of epsilon. Right, so any sort of given positive quantity that depends on epsilon, I can find a delta x which beats it, right? So in particular, I should allow myself a little bit of flexibility here if I'm trying to think ahead. Maybe this is not the setup I want. Maybe I want a slightly different setup with this given information. So I'll allow myself this C epsilon, which I'm going to go back later and fill in when I figure out how things are actually going to go in the proof. Okay, so I'll just have some positive constant C there, and I know I can do that. Okay, so the image we have here then is for, right, so we have this set K. So we have our set K. For every x in K, I can find a little delta x, right, a little delta x ball. So this is ball of radius delta x around x. With a certain property, right? All the function, right? If I look at the distance between f of x and f of y coming from this ball, then that's very small, right? But in any case, for every different x in here, I get a little ball around x where I have a certain property holding. And in particular, if I do this, right? So I do a lot of these. For every single x in K, I'm going to have one of these balls. Okay, so in particular, I have a cover of K. So the collection of open set, well, yeah, I don't need to say open right now. So the collection B sub delta x, x, where x is in K, is clearly an open cover. So is an open cover of K. Okay, and so you can see the figure. So I'll put this in a little box here. So you have open cover of K. All right, so this means that we're going to be able to find a finite subcover of this, right? Because of the Heine-Borel theorem. This gives us our equivalent characterization of compactness in terms of open covers. So by the compactness of K, we can find a finite subcover. So let's say it's going to be B sub delta sub xi, and I'll just call that delta I just for short. Okay, so there's only a finite number of these balls that are covering K. So clearly this is a step in the right direction. In particular, we could define something like delta to be the minimum of all of these deltas here, right? So probably your experience now with seeing a number of other proofs, as long as you have a finite number of quantities, you can take the minimum, right? So you have these finitely many positive quantities. The minimum is a positive quantity, and so perhaps that's going to be the suitable delta. But we should think about this a little bit and make sure we're even on the right track here. So right now, I'm sort of writing this as a proof, but maybe there's things I'm going to have to go back and edit later. I'm just trying to get down on the page sort of things I know and try to get the argument going in a good direction, and then we'll try to figure it out as we move along here. Okay, so we kind of need an idea now. We need to examine the situation and see if we're see how we can proceed. All right, so let's try to think about this. So we're going to have to identify a delta such that when the distance between x and y is less than delta, that implies that the distance between f of x and f of y is less than our given epsilon. And okay, so we have this x and y and k. We want to essentially, you can think about this as, if we're given an x, we want to say how close to that x do we need to keep y such that this inequality holds. So we're given x and k, then x is, because we have this open cover, x is going to be in one of, or we have this finite subcover, x is going to be in one of those balls. So x is going to be in some ball around some xi. All right, so I'm just going to give us kind of a generic looking picture. Like here's 3 of these balls, and let's say we have xi here, and x is in that ball. So what we want to do is say that as long as y is sufficiently close to x, then the distance between the f of x and f of y is close. Now here's one thing we can note. If y is also in this same x sub I ball, then the distance between f of x and f of y, right, so basically we know f of x is going to be close to f of xi, right, because being in this delta I ball, the condition to be in that delta I ball is that the images of the points, right, so the points in that ball from the center of the ball are less than some multiple of epsilon. So in other words, they're close together. Okay, so any point in this ball, its image is close to the image of f of xi. So basically, so that means the image of y is close to the image of f of xi, the image of x is close to the image of f of xi, and so their images must be close, right, by the triangle inequality. So this is less than or equal to f of x minus f of xi plus f of xi minus f of y, and we can make this less than epsilon as long as each of these are less than epsilon over 2. Okay, so that suggests that we should take this c up here, first of some number of edits that I'm going to make. So my c should be 1/2 there. So let's just change that, make that c a definite 1/2. So if c is 1/2, then as long as y is close enough to x to fall in the same x sub I ball as x, then the distance between f of x and f of y is less than epsilon. Okay, so as long as x and y are in the same x sub I ball, we can get our conclusion that we want. The problem with this is that there's no way to pick a uniform delta to put around, so what we're trying to do is put a delta ball around x and say that everything inside that delta ball, right, we're going to have this inequality. But the problem is there's no uniform delta ball that we can put around x that ensures that all of the things in that delta ball are also in this bigger ball around x sub I. Right? So imagine if I put a delta ball around this x, so this fixed x here, I can find a delta, right, so that the delta ball around it fits in that bigger ball around x sub I. And then all of the y's in there are going to fall inside this bigger ball around xi, and then we'll have this inequality. But the problem is this doesn't hold for all x, right? So I need a uniform delta that works no matter what x I start with. So I can find a delta for this x, but I need to find a delta that works for all x. And as I take x moving around, right, once I take this x and I move it, say, closer to the boundary, right? So if I take this x and I move it here, the same delta is no longer going to work, okay? Because now my delta is too big. I'm going to end up outside of this x sub I ball. I'm going to be in a different x sub I ball, right? And I don't have necessarily information about how far the images of the different x sub I are. All I know is that everything within these balls around the x sub I is close together, but I don't know about things in different balls. So that seems like a problem, right? We can really only make this work as long as the x and y are in the same ball around xi, but I can't find a uniform delta that works for every x in that ball. But we can force our way to a solution here by restricting the movement of x. Okay, so the problem is as x becomes close to this boundary, then no given delta is going to work, right, as x becomes close to that boundary. But if I restrict the movement of x, so if I restrict x to stay away from the boundary, then I will be able to find a delta that works. So for example, if I restrict x to stay within half of the size of this ball, and so I'll take a smaller ball, which is half of the size of this bigger ball. If I restrict my x to live in this ball now, then I will be able to find a delta such that the delta ball around all such x in this green zone, right? Think of this as like the habitable zone where we can always find a good delta. I can find a delta that works for any such x in here. So in particular, I can take my delta to be basically anything less than half of this this big delta I radius, right? So this green, so the radius on this ball here, that'll be delta sub I over 2, excuse me. So delta sub I over 2, and then my delta around x, as long as that's less than delta I over 2, that'll be fine, right? So as long as my ball around x is not bigger than sort of the rest of the way to the perimeter, then that's going to work. Right, so now this delta, as long as I make that less than or equal to delta I over 2, then everything should work out. So basically, what I need is I need to start with this x within delta sub I over 2 of xi. Okay, so what I really want, and so how do we get this x to begin with? Right, we just took an x and k and we said, okay, because we have this open cover, x is in the delta I ball around xi. That's not what I want, actually. So what I want, so what we need then is we need x to be in the ball of radius delta I over 2 around this xi. Okay, so what we really need is a cover of k by the delta sub I over 2 balls around x sub I, not the delta sub I balls. So what we need is to consider the collection of half radius balls up here. Okay, and then we'll get, and that's still going to be an open cover because every one of these balls contains the point x, right? So every point is still represented. Every point in K is still represented. This is still a cover, and so we can take a finite subcover. So what I need to do is modify my proof up here. Okay, so this proof is a little bit tricky because sort of your obvious moves here, they actually don't work. Like if you put an epsilon here, that's not going to work. You need an epsilon over 2. And if you just take the delta x ball open cover and then get a finite subcover, that doesn't quite work. You need to go back and revise and use the half version. Okay, so it's a little bit not quite obvious what choices you should make in the beginning. You have a lot of power to do things, it's just not clear how to exercise or wield that power. So you have to explore a little bit. So we have delta sub x over 2 around x. We'll consider that collection. So by the compactness, we can find a finite subcover. That's going to be the balls of radius delta sub I over 2 around xi. Okay, and now I think we have the ammunition we need to finish the proof. So what we'll do is, given x, so now I should pick my delta. So my delta I need to be less than or equal to delta I over 2, and I need that to be for any I. So I'm going to take delta to be the minimum of all of those delta I over 2's. So I need, in any one of these balls, I want my delta to be such that it doesn't reach out to the far end of the ball if I stay in the half radius. Okay, so we'll pick our delta. So once we have our finite subcover, we can choose our delta. So choose delta to be equal to the minimum of all of these delta I over 2's. So now, suppose, or maybe this is better phrasing. So choose delta equal to that, and suppose that x and y are within that delta of each other. Okay, we have to show that the f of x and f of y are within epsilon. And I'll keep the picture in case I need to reference it for now. So x and y are within delta. So since the half balls, right, so we have this finite subcover is a cover of K. X is in one of them. For some I. Okay, and then what we need, remember the key thing was that we wanted our x and y to be in the ball of radius delta I around xi. As long as y was in the ball of radius delta I around xi, then each of these, then we could use the triangle inequality and we'd have epsilon over 2 epsilon over 2's. Right? So as long as x is within delta I of xi, this difference here is less than epsilon over 2. As long as y is satisfying the same condition, we also have the epsilon over 2. So since that is a cover, and we have x in there, so we claim, or well, let's say in particular. So in particular, x is in the ball of radius delta I around xi. So the distance between f of x and f of xi is less than epsilon over 2. So let's say we also claim that y is in the ball of radius delta I around xi as well. And for this, we just have to measure the distance between y and x sub I. And remember, y is within delta of x. So this follows from distance between y and xi is less than or equal to distance between y and x xi. Remember, x is in the delta I over 2 ball, so that second term is less than delta I over 2, and distance between y and x is less than delta, so this is less than delta plus delta I over 2, and delta by definition is less than or equal to every delta I over 2, so it's less than this particular delta I over 2, or less than or equal to. So plus delta I over 2, which is equal to delta I. Okay, so then the triangle inequality, so then by the triangle inequality, and actually this segues seamlessly into the scratch calculation we did. Okay. So that's everything. And let me cordon off this figure here. So this was our brainstorming figure. Okay, so a little bit of a tricky proof, actually. Really kind of have to think about everything you've got and then figure out how to use it properly. In any case, that's the theorem. Continuity on compact sets always yields uniform continuity. So there's always for any continuous function, if you restrict it to, say, a closed interval, there's always going to be a uniform delta, which works for the in your epsilon challenge for continuity. And this is useful later. It's often used in the proof that continuous functions on a closed bounded interval have a Riemann integral. So the Riemann integral exists when you get around to defining all of that stuff. So this is one. So that's one place where this theorem is useful. Okay, so that's everything for this lecture, and I think that's going to be everything for chapter 4. So we'll move on to differentiability after in the next lecture.